Great. So yeah, my name is Luca Matteis, and first of all, I wanted to say how grateful I am to be part of this conference, to be talking in front of so many people that I admire. And just yesterday, I think at dinner, I sat next to Eric Evans. It just happened because there was a speaker's dinner, so I was really happy about that. But so my talk is a little bit, I would say, different than what I've heard so far, in the sense that I'm going to talk a lot about coding, actually. So, the main thing is, so this paradigm is called behavioral programming, is the main thing that I'm going to talk about. And I'm going to go very much in detail about how it works. It's a very specific way of programming, I would say. And but before I do, I actually wanted to say that it's something that I've been interested in purely because it's been a passion of mine. So it's not something that was driven by maybe my company, or I've never made money off of this. It's just been my pure passion for the past 2 years. And so the subtitle of this talk is Aligning Code with How We Think, because the paradigm is all about trying to think of programming in a different way. Use this thing. Okay. So before I start, the problem that this paradigm or this architecture is trying to solve is the idea that we've been sort of, over the past 50 years or more, we've been invaded by software. Right? Software is ubiquitous. It's everywhere. Everywhere we have software. And I think the main problem is going to come, already we're seeing this obviously in industry and research everywhere. We're seeing how software is really hard to understand and it's hard to change. So I kind of want to concentrate on these two dimensions, understanding and changing. And as a way of analogy, I think that the future, it's gonna, like we're just at the beginning in a way, even though everything is pretty much automated, but I think in the future we're going to have so much more of this. Everything is going to be driven. Think about robotics and space travel, whatever. And the image I have here is actually planet Earth right now. What those yellow circles are the sort of space debris that is surrounding our orbits, low Earth orbits. And I was reading an article about how actually it's going to become such, so there's going to be so much space debris that it's going to be hard for us to actually send rockets into orbit, because they're going to eventually hit, there's going to be so many that it's going to be impossible for us to sort of escape the Earth. And as a way of analogy, I think we're sort of maybe reaching a point in software development where things are so complicated to understand in terms of code, that we're hitting a similar kind of points where we either redo everything from scratch, or we're stuck with the mess that we have. So the idea of this paradigm is, again, to try to make the situation better, right? So to understand and to change code in an easier way. And just a simple outline of the talk is, so first I'm going to talk a little bit, so I'm going to dive really into detail. So forgive me if this is going to be boring, but I want to send the message across as I feel very passionate about this. And the second part, I'm going to kind of step away. So I'm going to try to go into details of code, then go a little bit upwards again, abstract all the details away, and think about how we think about complex systems. And then we're going to see how maybe we can align the way we code with how we think. And finally, I'm going to end with some research, because all of this is actually coming from quite respected or well-established researchers that have studied this subject. So it's not just me, obviously. I'm actually just I've done pretty much nothing. I've just taken what they created and presenting it. And then, of course, some cons, because all kind of new paradigms have some cons. And a little bit talk about the future. It's going to be kind of a challenging discussion. So, okay. In this section, I'm going to dive really into details, so please bear with me, okay? Don't fall asleep. But essentially, behavioral programming, the word behavioral stems from how we think of things like object-oriented programming, for instance, where even though object-oriented programming has a lot of baggage, right? It's a word that talks about a lot of things. But in essence, when we're doing object-oriented programming, the main units that we use when we're programming are these objects, right? And essentially, one explanation of how object-oriented programming works is this fact that we have these objects and they mutate each other, okay? So there's some state and calling methods of another class, of an instance, et cetera, et cetera. And then, of course, there's the sort of the big brother or the big brother of object-oriented programming, which is functional programming, which sort of continues on this idea, but everything should be sort of functions, right? So the main unit, what I want to concentrate here on is the fact that the main unit of programming in one way is an object, and in functional programming it's functions. And to continue this, in functional programming everything is pure, and the mutations are sort of put as much as further possible away from the thing that you're building, right? So behavioral programming continues on this wording, and in essence, forgive me for the image that I created, but in essence, the main units are not functions and objects anymore, even though, of course, you can use them. But the main units, so the main things you use when you're programming are these things called B threads, which actually stands for behavioral threads in the research. And these are they're essentially very close to what are real-world scenarios. So the things that we talk about, when we talk about our business, or when use cases, you can also call them stories. And here I'm depicting them as these lines because they obviously cross these boundaries. Whenever we talk about specific requirements or use cases, it is, in my opinion, very common to cross boundaries between, say, you have to change the authentication module and also the components in the UI, right? So these are different things that span multiple domains, I would say, and this is how we talk usually about requirements. So I was going to say that I'm going to dive into very, very much into detail, but essentially here, this is a screenshot from the paper about behavioral programming, and the way that it works is essentially that, so we program using these B threads, right? And these are these yellow boxes here on the left. And essentially all these B threads are running in parallel, okay? So that's one thing to remember. And they can essentially do three things, okay? They can request for events, and that is, triggering or proposing that you want something to happen in the system. Then you can wait for an event, so you can sort of listen to what's happening in the real world, or you can listen to what's happening within other B threads. And finally, and this is actually a crucial difference, is the fact that you can block events in red. And it's this idea where you can sort of stop things from happening, either in the real world or in other B threads. So this is the general mechanism. And then there's an event selection mechanism that figures out what needs to be triggered. So just to show you how this actually works, here's an example of a B thread. It's never mind the language, never mind the sort of syntax, but what is important and the point that I want to make is the fact that we are essentially using these request, wait, and block. So these are the main things that drive this approach, okay? And here what we're doing is it's a simple function, and also want you to pay attention to these sync calls, because they allow B threads to sort of peek into other B threads and figure out what's going on. Okay, so to go again into detail, I'm going to try to give you a very basic example. Okay, so let's imagine we have a simple program, right? And this program takes as inputs a number x, okay, depicted here as a constant x that it's reading the inputs. In this program, we want to understand whether it is multiple of 3, okay? So very basic, never mind, this is purposely simple, okay, just to show you the example. But what's happening here, okay, so we read the inputs, and of course, if it's multiple of 3, we return true, otherwise we return false. Most simple program ever. Now, imagine we want to change, again, this idea of trying to change the complexity stems from the fact that it's so hard to change software, right? So imagine we want to change this program. What we do, literally, is so the new specification or the new requirement is that we want to also check whether it ends with the digit 5. Very simple requirement, very stupid requirement, but just as an example. So to do this, of course, this is the only way you can do this change, right? You have to go in the code, change that if statement, you change the condition to also check, put an and there, and then have the function to check also whether it ends with digit 5. Pretty straightforward, right? Now, with behavioral programming, again, we go back to the example. So here, we're going to work with events. Even the program before worked with events. But again, we have these sync calls. And this is really the combination of these sync calls and this request, wait, and block is what sets this paradigm apart from the thing I just showed you right now. So we have this function, and here it's an infinite loop. And what happens is that here on the right, we have an event trace. So here, essentially, when we execute this program using this paradigm, this yellow line is depicting the execution step. So it's going to, of course, stop at this step of the function because it's waiting for the event number. It seems pretty clear, I hope. What happens is that when in the outside world, or whatever, we see that an event, of course, that matches number, the number is obviously matched. And the execution continues because, of course, we found that number. And because that number is 6, as you can see in the parentheses, it goes to the next step of the function, in which case it enters this if branch, because the is multiple of 3 is true. And at this point, again, we have the same step as before, a sync call, and it's requesting good. Okay, there's nothing surprising about this. So I'm still not at the interesting part, so forgive me. But again, the program is simply, as you can see from the trace, the input of the program was this number 6, and the output is good. So it just told us that 6 is a multiple of 3, right? Very basic. Now, let's go back, and then of course it goes back to the other statements. So now let's imagine that, as we did before with the other example, let's imagine that we want to introduce a change. And as before, the change is with this, we also want to check whether it ends with the digit 5. So here, the difference is that instead of complicating the module that we just wrote by adding the new and in the conditional, we are essentially making changes to the software by simply adding a new module, okay? And this new module is very similar to the one we just wrote. They run in parallel. But of course, the only difference is that in the if statement, right? One is checking if it's multiple of 3, and the other one is checking whether it ends with digit 5. Again, nothing surprising. And here I can continue the execution as before. Right? Maybe as a number for input, we got 5 this time. What happens is this yellow line is now connected, and I'll show you why. So again, number 5 makes both of them run in parallel. They both move to their own state. The one on the left goes inside the else branch because 5 is not a multiple of 3. And the one on the right stays in the first if branch because it is a multiple of 5, okay? But now the line is connected. And as I showed you before, these sync calls allow you to peek and see what's happening in other modules. And this is exactly what's going to happen here. What's going to happen is that they're going to all see their sync statements. So in this case, one of them is requesting, the one on the right is requesting good because it's in a good state for itself. The one on the left is requesting bad because it's in a bad state. But because it's also blocking good, as you can see here, that's the important part, it's going to essentially output, so the system is going to output bad, okay? So, again, sorry if I dove a little bit too much into details, but I think this is really important. The idea here that I'm trying to portray is the fact that we were able to introduce a change to the system without complicating existing code, okay? So you can imagine the one on the left was developed maybe by other teams or another person. Why do we have this thought in software that whenever we want to make changes, we have to complicate or add things that don't really pertain to that use case, right? The one on the left is, before I was thinking about the multiple of 3. Why do we have to complicate it with this, also the fact that it ends with 5? So we have this interesting separation. And again, here I have if I zoom out, as a program, this is a very simple example, obviously, but you can imagine a program being written with thousands of other modules, and on the top I depict these modules as being they kind of look like a bookshelf where you can swap out and swap in these modules, and they all communicate using this yellow line, this invisible line that is controlled by these sync calls. And intuitively, this system that I just described, even though it's a very simple example, what happens is that we can have new modules, and we can indirectly change how other modules work, right? So here, as the text shows, as goals are refined and requirements added to the program, or even when bugs appear, because you can even do the same trick with bugs. So rather than enhancing and often complicating existing modules, we strive to add new modules that precisely address the difference or the gap between the goals and what the existing systems accomplish. And I have another example, but I think I don't want to bore you to death. But essentially here I'm going to go to the other part, which is more abstract and interesting. But I have a similar example. So I have this program that has it's trying to control essentially the knobs of two, like water hot and water cold, and it's trying to produce water. And in this program and at this state, the output of the program is essentially that whenever the water is low, it's going to trigger 3 times hot, so it's going to release 3 times hot, and then after that, it's going to release cold three times. And what I'm doing here, this is the important part, is I'm adding, again, a new requirement, a new B thread that wants to change the system. And this B thread is called actually interleaved, because with this logic of sync calls and request, wait, and block, what's important is to see the event trace. We are essentially interleaving the two add hot and add cold without having gone inside the old modules and without having to complicate the way that they worked. They still remain, they still work as they did before. So again, this idea of incrementality where we can change code without going back. Okay, so sorry, I finished the deep dive. It took me almost 20 minutes. But now I want to with this intuition about how the system works with these kind of modules that weave through the program, I would say. So it's interesting because this is a quote from David Harrell, who's actually one of the originators of this approach. And he's essentially saying that in this approach, the modularity is not necessarily achieved by the structure, but can be done by these behaviors or these B threads. So you don't have to think of the system's behavior as being chopped up into objects or components or tasks. You can kind of chop it up any way you want according to the way you like to think about the behavior. And here I'm trying to depict kind of the high-level differences of this approach, where we may think of a system with low, on the left, with low cohesion, high coupling, which is something we don't want. And okay, the next best thing, what is it? Is high cohesion or low coupling, obviously. But this approach is really kind of, I would say, unrelated to this. It's there's these threads, right? These lines where they weave into one another, they overlap each other, they intersect, and they maybe say things that they forbid other things. And again, this idea that this idea of behavior versus structure. So at the top is this behavioral system where we have like a bookshelf where we can plug in new behavior as we want or as we see fit. And on the bottom is how we do it nowadays. We have these modules that create these really complex structures, and we kind of have to modify these pieces. And if we want to change something, it's like a Lego building. You have to take it apart and make sure the new pieces fit with their surroundings. So a lot more complicated. So here I have, just to let me drink and take a break, I have just a couple of funny videos. My friends were like, you should put some videos to not bore the audience entirely. And I'm pretty up to date with these kind of videos, but because I follow this Twitter channel, and but if you think actually it's not, the cat is okay. I don't know if you saw it. I'll show you again. The cat is perfectly okay, but because they always land on their feet, so it should be fine. But if you think this video is a little bit about animal cruelty, we can go the opposite direction. where actually what happens here is that I'll show you. The dog is going against the humans. Okay, so maybe now I want to back off, right? So I did a little bit of deep dive. So the second part of the talk is how we think about complex systems, okay? And I have this here just as sort of a reminder that I think in our field, so I'm sure there's a lot of developers here, right? How many people write code? Lift the hands. So almost everybody. So I actually think that coding is not really a science. So I'm going to try to explain that a little bit. I think it's much more. I'm not saying that it's as cool as being an artist, but it's kind of what I'm trying to say. Like, you have essentially. Here I'm trying to depict it better, but sorry. So, but we're essentially a craft because we're driven by emotions. We're driven by people that like certain things. You know, I may be more into like I have different psychological baggage, and I like to program and code in a specific way. My colleague that is reviewing my code has a total different history, but and we expect sort of us to work with the same tools and paradigms. I think it's a lot more like painting in that sense, where for different people, specifically here I show an example, right? So there's so many architectures, right? There's so many patterns, there's many. So I make in bold there behavioral programming, the thing I'm talking about, just to show you, okay, how is this different from all the rest, right? It's just pick and choose whatever fits your character. And in fact, I'd argue this is what we mostly do. It's very emotional, right? Like maybe the person here on the left is more, imagine they have more of a scientific background, so they want to pick specific patterns or architectures that are aligned with their way of thinking. And on the right, maybe we have a more creative person, that is more into music and they like to read things, maybe they like, event-driven programming or proxy or other things, so many of them. So why is this approach, how does it stand out, And so again, instead of having these arrows inwards, so having all these paradigms and we have to pick and choose whatever fits our, essentially our brain, if you think about it, or even our problem, obviously. But I actually think that the problem becomes secondary. We usually pick and choose the paradigm based on our personal preference. It's very subjective. So what if instead we do the opposite? What if we just kind of think about what is the paradigm that best fits our model of thinking? So we kind of find what is the common ground that we are all, sort of our minds work alike, even if you're a creative person or a technical person. And then we kind of build, so bottom up instead of being top down, right? And if I can give you an advice, is to read this paper. It's called The Quest for Runware on Compositional, Executable, and Intuitive Models. It's an amazing read, I think, from 2012. Again, by this professor called David Harrell and Asaf Moran. And Harrell is actually the creator of state charts. If anybody is interested in state charts, has been de facto standards for the past 30 years. It's visual language. But anyway, so we have this dichotomy, right? So he depicts this mountain. I think it's a very good analogy because, so on one side, on the right, we have us, humans, right? And on the left, we have the computers, right? So it seems like software development is a constant effort of trying to dig this tunnel. And what I mean by that, or what they mean by that, is the fact that we have to sort of, whenever we have to program, or whenever we have to talk about computers in general, we sort of have to think like the computer, right? We have to change our minds to think like the computer instead of, so we dig the tunnel towards their direction. Why? Like, why can it not be them coming towards us more? Because computers are intelligible systems. We can make them do interesting things with the artificial intelligence. They can do more things like this. Okay, so to show you how we can actually, so sorry, again, now here I'm going to try to not think about how we code. I'm going to try and think a little bit about how we develop systems in general, or how we think of systems, even without a computer, even though I'm going to draw the analogy. So to do this, I'm going to try to discuss how we would develop a tic-tac-toe game, okay? And on the top left, I sort of depict the requirements world. So these are the people that kind of are non-coders, you would say. And then on the right, the implementation world. And I think this is the economy of sort of the behavior versus structure, which if you can keep an eye on when I talked about the B threads before, there's a lot of analogies here, obviously. So, but anyway, and it's also important that I'm the time, because as things happen, even in the requirements world, we see things change drastically in the implementation world. And I'll show you this. So we can say that, for this game, the first requirements would be to detect wins. Very simple. When a player places 3 of his or her marks in a horizontal, vertical, diagonal line, the player wins. Very basic, right? And in the implementation world, also please keep an eye on the colors, so they're color-coded. We create a bunch of functions or objects or whatever. As we continue with the requirements, in force turns, of course, the structure on the right, the implementation becomes more complex. Here, it's already quite aligned. I wouldn't say that it gets too complicated. But obviously, you can imagine, I don't know if you can see the color. Oh, shoot. If you can, sorry. If you can see the colors, so every time we add a new requirement, what happens is that maybe other section of the structure have to change, obviously, to sort of fit this requirements, right? And we end up, essentially, so this is the system finished. We end up intuitively with really 2 different worlds. On the left, we have these documents that talk freely about the system. And they're quite detailed, these requirements. So, I mean, for instance, the last one talks about how you can foil an attack, so you prevent an X from winning or an O from winning by putting it in the right box. But it's quite, just at a glance, so the first thing that comes out is that the requirements that talk about a specific thing is contained. So, start at center is a contained piece of information, whereas in the code it's lost, in my opinion, it's lost in the structure. So for instance, the pink one, the last one, we find it in the center, at the bottom, at the left, at the top. So imagine having to sort of figure out where that requirement, how can you figure out whether a requirement is implemented in a system or not? I mean, I would argue it's really hard nowadays, right? It's okay. Another apparent difference, I would say, is this idea where so the requirements are actually, I would say, they're quite independent. And what I mean by this is, again, going back to the B threads. Every time I mention these things, you can go back to the examples I made in the beginning. But the requirements on the top left, they're not connected by any arrows. There's no arrow, a line connecting any of them. So this was, when I first saw this, I was like, yeah, it's interesting, right? Why is it that we sort of, they're independent. So I mean, forget that the line is just, of course, a visual distinction, but the idea is that there's no connection. Whereas in the implementation, everything is connected. And the reason it's connected is because the structure has to abide to the computer, the way the actual mechanics of the computer works. So the computer has to execute your function. There's a call stack, subroutines, state. All things that we are used to thinking is normal. And they're not really, a stack trace does not appear in the requirements world. It's a relic or a historical, I wouldn't say a mistake, obviously, but it's there because that's how computers work, okay? But it doesn't appear in the requirements. And again, this idea where abstraction does not imply hierarchy. So we have this thought that whenever, so by abstraction, I mean the idea of when we abstract something away. So removing details to better see the large picture, okay? That's my definition of abstraction. And again, in the requirement world, even though this is a pretty simple app or a simple game, I would argue that there's none of these views in the requirements world, none of these views or requirements, there's no hierarchical connection between them. So even though, for instance, the start at center, sorry, start O at center is actually quite specific and quite low level, it's not hierarchically connected to other views, okay? Whereas in the implementation world, in the structure where we have these objects, functions, and code, there obviously are. There's this hierarchy. And one of the most important differences, I believe, and I hope I can explain this, is this append-only idea. And what I mean by this is quite important, I think. Like really, so the idea is that, again, in the requirements world, new requirements are piled atop, you know? There's no component interface between the requirements. There's no connectivity, there's no ordering. We kind of, whenever we want to change a requirement, so imagine you have a pile of requirements on your desk, right? If you want to change how the system behaves, you don't, you kind of write the new change that you want the system to have, and you kind of put it on top of the sort of, you know, list of requirements that you have. You don't actually go in the paper, find the section, change the wording, but that's actually what we do in code, okay? So again, this idea where we can, on the left, we're adding a new requirement. This is a change. We want to stop the game after a win. Pretty simple change. And in the implementation world, it's quite different. This change requires us to peek and look in different modules, as you can see again for another requirements. And one of the last important differences, I would say, between these two worlds is the fact that there's this idea which I call upfront negativity, okay? So this is also hard to explain, but imagine you're able to, so in the requirements world, what we can do is we can say, I want to stop the game after a win, okay? Now, the interesting thing is that we can say this at any point of the development. We can even say this at the very beginning, even before having to, even before we wrote any line of code that involves the game logic. We can say, okay, I want to stop the game for win. So imagine that sort of this is quite interesting. We cannot really do this in code. We have to, again, this is the same change implemented in red here, these red boxes, if you can see them. This change cannot be upfront. There would be no arrows connecting these boxes. A little bit hard of a concept to understand. But imagine we have these, I can move to the next one, which actually explains this a little better. It's this idea of multimodality, where we usually in the requirements world, we're able to specify we specify what may happen. So what may happen in the system, okay, the red ones, we can enforce turns, we can start at center, the square is taken, and then we specify what must be done and what must not be done. So essentially specifying these two things will constrain the execution of the program. And this is, again, going back to the block of the B thread that I showed you in the beginning. And this is, it shows also in the way we do requirements. We first specify perhaps the constraints. Imagine specifying the constraints of the program and then building on top of that. That's, I think, very powerful. And again, overall, there's this idea of natural programming, right? Something that feels natural is this idea that modules are kind of interweaved, right? How we show you here with these laces. And another example is this, we might have a module doing, taking care of a trip, the directions, another one of the day schedule. And the day schedule is stopping the car. It's driving again, but it doesn't connect directly to the directions. They're interleaved in the same way that I showed you in the beginning with this yellow line and these sync points. And again, so if now we introduce the behavioral programming to the system that we just wrote, we can see that these requirements, as they're added, they're very much aligned. So this is the implementation world, okay? And this is actual code that runs and works. I have at the end, I have some material. You can actually use it on a web page. And what I like to highlight is all the things that I talked about. The fact that they're in the implementation world, that there's no, they're all independent, these units. There's no arrows. There's really no structure, actually. So there's no hierarchy. They were done in this append-only kind of fashion, the same idea as requirements. And this idea of also upfront negativity. So here I have a small video of the game in action. And by upfront negativity here is the fact that as you can see, the user is placing, but now they're trying to place an X after another X. And this essentially is being enforced or blocked by this thread. So there's this idea of upfront negativity. So imagine implementing this in the normal way. I would argue that you cannot do this upfront. You have to go inside the structure, figure out where the O is drawn, and conditionally put maybe an if statement around it or something like this. Here I have another video of temperature rising, a simple UI. So there's an increase of 10 times, an event increase is called 10 times, and it rises to 100. There's also a decrease event. Now let's imagine there's a new requirement that pops in and says, I don't want the increase to happen immediately. I want it to happen with sort of a throttle time. So it kind of gradually increases and gradually. So instead of going inside the code that we just wrote, or even instead of knowing anything about the system, I can write these two B threads that essentially block the increase after a certain time, and the effects are essentially what you want. And here I have another simple video of essentially a simple web app where you can see some movies and then click on them, read the reviews, all written in this kind of behavioral programming fashion. And what it really is interesting about this is that here you can see the trace of events that happen within the system, like maybe the person clicked the movie, it rendered the index page, the movie is highlighted, et cetera, et cetera. And what's important is that at any time, a developer can come into this project without even knowing how it works, and it can use the trace and say, okay, these things, I don't want them to happen. And they can simply take those list of events that they don't want to happen, and they can write a B thread dedicated for that use case that actually blocks that list of events. They don't have to go in the structure and figure out, okay, where does this event happen? Where does the event? Okay, so just to conclude, I want to go kind of here again, and this is from the paper Runware that I think is really great. But if we think about how our brain works, so I can read this a little bit. So there is essentially no modification of existing initial memories, no insertions, no cut and paste, only more and more experiences, okay? So there's no insertion, no cut and paste. So images seen, sentences heard, pain felt are all amassed as new memories and are connected to existing memories in more ways than we can imagine today. Some of these, of course, explain, refine, correct, reorganize, or completely replace things that were previously experienced or seen or heard or read, and how they affect future behavior. So, of course, it's very similar to the things that I've talked about, right? But I think what's important here is the fact that our brain really does not have insertions and cut and paste. We have, which are things that we do in programming, right? Whenever we have to change or whenever there's a new idea, we have to go in the structure, cut and paste, change it with something else. Instead, our mind obviously works quite differently than that. Okay, so just to finish on some resources and some thoughts, I have a research section. If you want to know a little bit more about this paradigm, you can simply Google search behavioral programming and then Harrell. It's the last name of the professor. There's a lot of research. And it's actually, so this one is theoretical, where they study this request weight lock model, and they actually prove that it's a little bit more succinct, smaller in state space for the technical people. On the right, there's actually a little bit of empirical evidence, which is interesting, coming from software development. We don't have a lot of empirical evidence. But essentially what they do is a small study with the high school people, where high school people don't really, they have no programming backgrounds, and they compared this system with a traditional programming system. And the results, of course, are a little bit biased because the creators performed the experiment, but they were in favor of actually something like this behavioral programming. And of course, there's cons. So what I did is I told you that this has been my passion for the past 2 years, and I've written some some blog posts essentially. And I don't know if you know, this website is called Hacker News. So there are very valid comments. When I posted these articles, they commented in a very, I would say, realistic way. And some of them are talking about how the fact, this can become, all these threads, all these modules together they can become a big ball of mud, right? So it's complex and convoluted, it's impossible to understand, right? And this is a general theme. How can you understand? And in fact, I agree with this. And what I can say here, so what I'm trying to say here is that, so this approach comes with some cost, right? For instance, as I showed you in the beginning, if you remember this idea of two modules being is multiple of 3 and it ends with digit 5. So having these two together in the same function is very easy to understand when you're debugging. But having them in different modules, it's a lot harder. So personally, actually, this is very true, and it is a con of the approach. But I see this more as a trade-off. So in a way, it's kind of trading control flow for extensibility. And at the bottom, I kind of try to depict this trade-off, which I think, to be honest, should be applied to any kind of architecture, right? So this idea where all architectures work, whatever is your problem. I don't think it's not true, because I feel like if I work for a startup, I'm developing software in a completely different fashion than if I'm working for NASA, right? And because the startups are experimenting, they want to develop something quickly, put it out there, let it test from the users, and then kill it as soon as possible if it's not working, right? So something like this, I feel, something like behavioral programming, to be specific, I feel is much more appropriate in a world where there's requirements are changing constantly, which feels a lot like startup world. So I feel it would be more appropriate to have it there. Where something like NASA, as an example, it's something rocket science. If you're building software for a rover that has to go to Mars, you want something maybe less that doesn't change often. You need an architecture that connected to that. And a little bit of words about the future, and then I'm almost done. But there's some other things, like if you want to get into detail about this approach, so the sync point that I talked about in the beginning, it's not just this idea of request, wait, and block, but they're going even further. There's active research on this right now, where they're actually using constraint solvers to figure out how to have the B threads precede their executions. And this is quite interesting, because what happens is that the computer is faced with multiple possible execution paths. And the way that it chooses one path instead of the other is they show that it actually it involves certain properties that are a little bit, how to say, you wonder if it's kind of like the free will of computers. But and then there's also graphical languages for this, actually live sequence charts. So each one of these boxes, these 3 boxes at the center, is one B thread that represented visually, let's say. And there's other ways to combine it with this other language called state charts. And I want to end, I have 15 minutes, but I just want to end with this idea of what I call, actually this is my own, nothing research about this, but this idea of what I call chat-oriented programming. So let's imagine that we are developing software. It's not about having to go through an artifact that we call code. So every time we want to make a change to a system, there's always this code in the middle, right? We actually use the piece of code when we have to open an editor, open the code, and the code, so the changes that we make in this structure, this graph, represent the changes that we want the system to have, right? I would argue that maybe in the future, possibly with something like this, or behavioral programming, or something else, who knows, I'd argue that we don't need this artifact anymore. We still need the code. We still need to code, but our relationship with changing and also understanding the system, it's not going to be through a two-dimensional piece of code. It's not going to exist anymore, in my opinion. It's going to be much more of a chat. So imagine you're the person on the left, you're the programmer, and on the right you have the computer. So you have an interface that is much more like a discourse. And I'm not talking a discourse in terms of natural language processing, okay? Not at all. I'm still talking about code. But you're sending the system code instead of changing a large structure. And in this case, for instance, imagine you want to tell you're observing sort of on a vehicle, what's happening in the software of a vehicle. And you ask, when the driver presses the brake pedal, the light should turn on. And you encode this as a B thread, or several B threads. At the bottom, you have these sync points, right? And then you send this to the system, okay? As a sort of, imagine a chat message, which is based on code. And then the system comes back with a visual, I don't know, maybe a plot, a live plot showing you, okay, these are the times that it happened, that I found it happened when I did some, when I ran the system 1,000 times. I found these are the points, and there's red dots where it happens. And you can interpret this graph as meaning something like, does it also apply when the engine is off? And then you say no, of course, through code. And you can have this conversation. I'm not going to go into detail, but you can say, why didn't the brake light go on? So the only way we currently have to answer a question like this, in my opinion, is, again, having to go through the code. That's, of course, we have documentation, we have models, but at the end of the day, the devil is always in the detail, right? So the language, the programming language, is the barrier to understanding what is happening within the system. And why do we have to fight our way through the structure, right? Why not have this sort of discourse where you ask, okay, why did it happen? Okay, tell me using another interface, So this is what I envision the future to be like for software developments. And I can skip this. That's pretty much it. This is just a final idea about a HRL, again, where the units of specifications are not assembled in detail like resistors or chips on a computer board or methods in an object-oriented programming language. It's this interweaving of these modules that will be sort of the actual program. And I want to end again on this slide because, it becomes, with the system, in my opinion, it becomes a little bit less blurry if you're starting to think in terms of what your use case is or your scenario. Do we even need these boundaries across these systems? So yeah, this is pretty much some further reading. I wrote these 3 articles myself, but again, all the things that I wrote are entirely based on research done by these 2 professors and other actually people. I think they're based in a university in Israel. It's called Weizmann University. And that's pretty much it. Thank you for listening. If you want to have any questions, I think.
We have a few more minutes for questions. So if anyone has a question, we have a mic box in the room.
Can you please pass? Question?
We would like it in the mic box for the video.
Can you hear me?
Yep.
I was just wondering how testing paradigms change using behavioral programming.
Sorry, testing paradigm change?
Yeah, just how you would go about testing your program, how that would change, if it would change, or how it would change using this new way of thinking.
Sure. So I would say testing is a little bit different for sure. I would say that testing a module independently, so the idea of unit testing, is a little bit unclear, because what happens is that, of course, once you put it in the system, there could be another module that changes the way that it works, because that's the idea. So I would argue that actually unit tests are a little bit more blurry how to do them, so that's probably one of the cons, I would say. But in terms of testing in general, you can still test the whole bunch of B threads, and because that's your program, and you can just test events as inputs, and as long as the system produces outputs other events that you expect, there would be sort of your integration tests, I would say. But it's, I agree with you that it's a little bit blurry how to do the unit tests, for sure.
Thank you.
Oh. Yes. Oh, nice.
Hi there.
Hi.
My question is there ever been anything built that's more than trivial? Any program?
So there's, from me personally, no. Sorry. But there is a lot of research, yes. So the team of researchers They have built a lot of things like even low-level things like web servers, highly distributed, actually, sorry, not distributed, high-frequency web servers with a lot of requests coming in, and entirely using this model. And they have a paper that goes a lot in, it shows you the code and goes into detail about the pros and cons. So yeah, but not, I would say maybe your question is more in industry, not in, I haven't seen a company use this. I don't use this at work myself. I just, yeah.
Can I ask a follow-up question?
Sure.
How would you say that you deal with removal of behavior? Let's say we know about technical debt and we know that there's something in the model that does not fit reality anymore and you would want to get rid of it.
Sure.
I understand if I watch this that you never ever remove anything, it's just addition, but how does that scale?
Yeah, so essentially you can think of it in two ways. You can think of it either as if your model changes in the real world, I would argue that it's better to make sure that your B threads are aligned to that reality. However, it's true that you can go ahead and change the module the same way that our brain works, right? You can go ahead and tell the system about how the new model works, or the new world works. And you can do that without having, you can also do that without having to go back and change the B threads. And you can do that simply by saying, okay, I want to stop these things from happening, sort of with, I guess, with the block semantics. And that's going to essentially, the B threads are going to stop working, and there's maybe ways to optimize that where they're removed from the system entirely. And then your new B threads, which represent your new reality, will simply function and make the system work the way you want it. But there's still big questions regarding that for sure.
Thank you.
Okay, one last question maybe? Nope.
Okay.
No one?
Thank you.
Thank you again, Luca.